Okay, welcome to lesson 16, our last lesson of the week. We are going to talk about random variables. We're going to describe what they are and give a couple of examples and do an intro to probability models. We'll look at uniform random variables this week. Next week, we'll start looking at normal random variables. So a random variable, so we abbreviate it RV. I had one professor in particular that always used capital letters. It doesn't matter too much, but it's a quantity that takes on some real number value for every event in the sample space. So if I were to talk about let x equal the sum of two dice. So I'm still looking at the six-sided dice. X could equal 2, it could equal 3, 4, 5, and so on, all the way up to 12. That's the idea, like that. So every single value has a likelihood, so there's a probability that I roll and I get 2s. There's a probability I roll 2 dice and I get a sum as 5, and so on. And we call these random variables because from roll to roll, well, if you're using dice, it can change up every single set of rolls. So there are going to be two that we focus on. We look at discrete variables. So a random variable, you can describe it as discrete if it has a finite countable set of values. Honestly, if it looks like you're counting, so like 0, 1, 2, 3, up to a certain number. Usually there's a cutoff. Where it's going to represent whole numbers most of the time. So usually it will be start at 0 and then go 1, 2. You can't have 2.5. You can only have whole numbers here. Usually like they're counts of things. And then for a continuous random variable, it's going to be continuous. Oops, I can spell some days. If it takes on all values over a certain range. So I can have, like, say, heights. Somebody could be, 68.23 inches tall. You don't have to only be, you could be 63 or 64 inches tall. No, you could be 63.6 inches tall. So it can be infinite, like anywhere in between there. So I want to point this out. So suppose I have a variable of interest I'm collecting and it's categorical. I'm going to focus on eye color, right? So I'm going to ask 20 people their eye color. The random variable that goes along, almost always, at least in this class, it's going to be a count. So I'm going to pick number of, and then it could be any category. I'm going to just pick one, brown eyes. So if I take a random sample of 20 people and I ask them their eye color and count the number of brown eyes they have, so, or number of people that say they have brown eyes. So I can have 0 people say they have brown eyes. I could have 1, I could have 2, all the way up to 20. You can't, if you ask 20 people, you really can't have more than 20 of those 20 people have brown eyes. So then quantitative, oh, I wish I had changed this. I do not know what brains typically weigh. So example, brain weight. So usually we use capital letters for random variables, and usually they're capital letters at the end of the alphabet. So X and Y and Z, they're really, really common. So Y is my random variable, and it's just going to be brain weight. The quantitative variable of interest is the same as your random variable. It's just going to be the same. For categorical, you're going to pick on a category. So if it's eye color, number of brown eyes. in your sample. And the idea is if I ask 20 people, the number of people out of those 20 that have brown eyes will change every single time I take a new sample of 20 people. That's why it's considered random, because it changes every time. Same with here, like the brain weights of people will change every single time I take a new random sample of 50 people. Okay, so we're going to start with finite probability models. So when we have a discrete random variable, we want to list all of the possible outcomes we can get. So if you said x equals number of brown eyes out of the 20, you can get x is equal to 0, 1, 2, all the way through 20. What this finite probability model does is it's going to list every possible value it could be and the probability that you see it be that value. So, like, hey, what is the probability that you ask 20 people if they have brown eyes, and 0 of them have brown eyes? So there are some important rules. All probabilities here, they have to be between 0 and 1. They can be equal to 0 and they can be equal to 1. Just know that it's not as interesting if that happens, because if it's equal to 0, it means impossible, can never happen. If it's equal to 1, it means it always happens. Most things fall in between. So if you add the probability, so if I add the probability that 0 people have brown eyes, that 1 person, that 2, that 3, all the way through 20, all of those probabilities will add to 1. And then these probabilities are disjoint. What that means is if I take a random sample of 20 people and I get x is equal to 2, that means 2 out of the 20 had brown eyes. It means that x is not equal to 3. X is not equal to any of these numbers except 2. It can only be 2, right? So it's only one of these values at a time here. So for example, we have, they're looking at the demographics, specifically age demographics of online students. So we have Dr. Mendoza, they go ahead, they survey 5,400 online students. That's a handful. I think, I'm not sure how that compares to Oregon State's, especially lately. So the results are as below. So we have, they went ahead, they put them in groups. So 18 to 23 years old, it looks like 3,078 of them, of the 5,400 students, were in that particular age group. And so then they have the number in each age group after that. So if I want to put these into a probability model, the first thing I need to do, I need to grab my categories. So people in, the youngest age group, people in the second youngest, third youngest, and fourth youngest. I need to make them here. So here are each of my categories. So the probability, it's going to come down to, if I have these 5,400 online students and I randomly select one, what's the probability that I randomly select somebody that's in the 18 to 23 years old group? So I'm going to look at, well, I have 3,078 of them out of 5,400. Let me see. Going to get something like 0.57. So 57% of these online students are in the 18 to 23 years old age group. And then I'm just going to repeat for the next age group, 24 to 29, 918 out of still 5,400 students total. I am not doing this in my head. I threw this onto my calculator. So it looks like 17% of the online students are between 24 and 29. So then we have 756 out of the 5,400 that are 30 to 39. So, oops. It's about 14% or 0.14. So no, these are all between 0 and 1 so far, right? Can't have negative, can't have above 1. If you see a negative or you see above 1, that should be an automatic, like, this is not a legitimate probability model. And then the last one here, so 648 over 5,400, it's going to be 0.12. So here, they're all between 0 and 1. And check it out. If I add these four numbers together, 0.54 plus 0.17 plus 0.14 plus 0.12, I should get 1. Note, it's not a legitimate probability model if it doesn't add to 1. It should add to 1. Every once in a while, because of rounding, it's a little funky. But this is nice and friendly. I actually didn't round any of these numbers, so it should be okay. So in order to be a legitimate probability model, you should have, disjoint categories. So if a student is in the 18 to 23-year-old age group, they can't also be in the 30 to 39-year-old age group, right? They can only be in one category at a time. All the probabilities are between 0 and 1. And when you add all those probabilities up, you get 1. So, legitimate probability model, it looks good to me. So here, is this a legitimate? Yes. So, 1, we have disjoint categories. You can only be in one of these age groups at a time. At a time. Right? So you can't have a person who's in the 40 plus group and in the 30 to 39 group. They can't. So 2 probabilities are between 0 and 1. So all of these are between 0 and 1. And then 3, sum of the probabilities. So when you add them all up, is equal to 1. So now that we have this legitimate probability model, we can use it to find, probabilities. So suppose I want to randomly select a student from all of these online students. I want to know the probability that I have an online student that is 30 or older. So probability 30 or older. So that's going to be the probability. They're 30 to 39 or 40 plus. So because I know that these two categories are disjoint, right? You can't have people in both groups. I can just say, that's the probability of 30 to 39 plus the probability of 40 plus. Oops. So I can just take that 0.14 plus 0.12, add them together. So about, it looks like 26% of the online students are 30 or older. And then C, what is the probability an online student is not 18 to 23? So probability not. I'm gonna call this A, B, C, D. So not A. So A complement. Right? So there are 2 ways you can do it. So 1, it's probability that 24 to 29 plus the probability, so you can add these three, right? So you don't want this one, you want these three. So 30 to 39 plus 40 plus, so 17 plus 0.14 plus 0.12 should come to something like 0.43. Definitely check my math. The way I did it was I used law of complements. So what I focus on is I didn't want this one, I wanted everything else. You can say it's 1 minus the probability that they're in the 18 to 23 age group. So you can say it's 1 minus 0.57, which is how I actually did the math so quickly on the first one. That's just going to be 0.43. These should match. If you are doing this at all and they're not matching, something went sideways somewhere. So definitely here, when there's only 4 categories, it's not too bad to add 3 numbers. But every once in a while, you'll see like there's 20 categories. So you can add 19 categories, or you can just take 1 minus just the 1 category. It's a lot easier to do sometimes. So student emails. So we have a large survey, and they went ahead and they asked students how many times they checked their email in the last 24 hours. So they have the following probability model. So X is the number of times they checked their email in the last 24 hours. So you had some folks that checked their email 0 times, once, twice, 3, 4, and apparently you didn't have anybody check their email more than 4 times. So they definitely did not, survey me. So, I mean, just things to check. If they checked their email 0 times, they didn't also check their email 3 times in the last day, right? You can only be in 1 at a time. All of these numbers are between 0 and 1, and when you add them all up, it should equal 1. So now that we have this probability model, we can ask questions like, what is the probability that we randomly select a student from whatever population this is, and the student has checked their email exactly 3 times? The probability that X is equal to 3. So just line it up. That's all it's going to be, is that 0.25. There you go. So B, what is the probability of randomly selecting a student that has checked their email 3 or more times? So probability X is 3 or X is 4, right? Because 3 or more times, it includes 3 and it includes more. The probability X is equal to 3 plus the probability X is equal to 4. So I'm just taking these 2 probabilities and adding it together. So 0.25 plus 0.23 is going to be 0.48. So if I were randomly selecting a student from this population, there is a 48% chance that I'd select a student that had checked their email 3 or 4 times in the last 24 hours, according to this probability model. Since going remote, who knows? I feel like, especially with email being on phones, people check it, I think, honestly. Sometimes many more times than that. So continuous probability model. So we were talking about discrete. We're going to introduce continuous. So the idea is the probabilities between 2 values. If I add up all of this area right here, it's going to always equal 1. We're going to have some specific examples. So we are going to talk about the uniform probability model today, and then we'll introduce the normal distribution next week. So just a quick, the uniform distribution, it is simple as it gets. It's a giant rectangle. That's it. It's a rectangle. And the area inside of it is 1. Makes it nice and easy. So constant probability. So probability between 0 and 1, it's just this same probability. It's the same as between 1 and 2, the same as between 2 and 3, between 4. That's the whole idea. That is one constant or uniform probability. Then the normal one, so even if you don't know stats, chances are you've seen a normal curve somewhere. They are incredibly popular. Definitely saw folks trying to fit curves, normal curves to like COVID outbreak curves. That was interesting. So these are like the superstar / like maybe a little slightly overrated in stats. Definitely the most common that you'll see anywhere. It's bell-shaped, so I mean, I don't know. I don't have many bells around my house. And it's perfectly symmetric. So both of them are. The idea if it's perfectly symmetric is you draw a line down the middle and you fold it in half and it looks exactly the same on both sides. So I can't draw perfectly. So same on this side as on this side. It's a mirror image. So the uniform distribution. It models a continuous random variable between 2 values. So from point A to point B, there's constant or uniform probability between those 2 values. So they all have equal likelihood of occurring, and it's symmetric. It's shaped like a box. Anytime you want to draw a uniform distribution, just start with a rectangle. That will be the first place to start every time. And they're really good for modeling things like random number generators, because if you have a random number generator, any number is equally likely to be selected. That's the idea. So one example that we'll end up using, we have a large conference room that we're definitely not allowed in it now at a university, and you can reserve it anywhere up to 4 hours. They won't let you reserve it longer than 4 hours. So there are a lot of meetings, they occur really often, and they have all sorts of, they can be really short, they can be really long. So we can model it with a random variable x. So x can be the meeting times, or meeting duration. And it can go anywhere from 0 hours to 4 hours. Although I have to admit, it's probably not worth reserving the room for 0 hours. But, you know, you can. So we can model it this way. And as you can see, like, it's not quite actually exactly this rectangle, but the rectangle is a really, really good approximation for it. So using that example, so it's said to have a uniform probability if the probability of these outcomes are the same. So if it's level, if it's flat, that's what it comes down to. Uniform or constant probability, it's flat. It's not going anywhere. So A and B, they represent the endpoints. So this will actually be a number, this will be another number, and you have constant variance between them. But suppose, what's cool is, so this is a rectangle, so this is just B minus A, whatever this length is. And then this height is so B minus A times 1 minus, it's just 1. So that's how the area under the entire thing, this entire thing has an area of 1. So the trickiest part most of the time, so you find out how long it is, and that's going to tell you what the height is going to be. So like if this was, 5 long, this would have to be 1/5 tall. That's the idea. But then suppose that I want to find a probability in between on here. So I have so little a and little b, and I want to know this area. It's really cool because it's just the area of a rectangle. So this is little b minus little a. We still have the height, so 1 over b minus a. And that's just the area of the shaded part right here. So absolutely feel free to use these equations. For me, it's really easy to go, oh, I can find the area of a rectangle. So whatever floats your boat here. So we're going to use that conference example so that they can reserve for a meeting anywhere between 0 and 4 hours. And we're assuming that the length of a meeting is a random variable and it has a uniform distribution, anywhere from 0 to 4. So the first thing I hear uniform, I'm going to draw a rectangle. This is not the prettiest rectangle, but I mean, without a straight edge. So from 0 to 4. And since this is in hours, I am going to write hours. It is a little important here. So I have almost everything I need. So things to consider, I want to know how long this is. So 4 minus 0, that means my rectangle is 4 long. So my height, it's going to be 1 over my length. So 1 over 4. Because if you have 1/4 times 4, that's just 1. And that's the area of this whole thing. It's 1. Goofy looking 1. So from there, we can ask how likely is it that a meeting will be less than 1 hour. So I'm going to draw on here to make it easier for me to see. So from here is 1, and I want to know that area. Well, for me, for starters, I'm going to say, okay, well, I know that this is 1/4 tall. How wide is it? Well, 1 minus 0 is 1. So I'm going to get my probability equal to 1 times 1/4. It's just going to equal 1/4. So there's you could put it in decimal as well. There's a 25% chance that it'll be less than 1 hour. So then, for my part C question, how likely is it the meeting will be longer than 90 minutes? Well, I have this axis in hours, this is in minutes. You can switch it. You can either switch this to minutes or switch this to hours. So 90 minutes happens to be 1.5 hours, exactly. So for me, it's 90 minutes is 1.5 hours. I'm going to switch this to hours. It'll make it easier for me. So 1.5. And they said, okay, well, how likely is it will be longer? So what they're asking really, so what's the probability that it's between 1.5 and 4 hours, right? So I know the height already, it's 1/4. And I can find the length, right? So 4 minus 1.5 be 2.5. So if I want the area of this rectangle, it's going to just be 2.5 times 1/4. So at 5 halves times 1/4, 5/8, which is it's been a while. 62.5% or 0.625. Definitely double check. There we go. So if I were looking in here, 62.5% of all of the meetings could be longer than 1.5 hours. But longer than 1.5 hours, just remember it does translate to still less than 4 hours. Just like this one, you could say, oh, well, that's less than an hour. It's the same probability that it's higher than 0, but less than 1. Really, that's what it comes down to. So voltage, this one can be fun too, right? So we have a random variable x. So x is the voltage in a circuit, and it varies anywhere from 8 volts to 13 volts. And we're going to assume the voltages are spread evenly, so this is what gives away the uniform bit. Also in addition to that, over the range of possibilities. So the first thing I'm going to write, so volts. And I have, it goes anywhere from 8 volts to 13 volts. And note, once you go past 13 volts, the probability is 0. Once you go lower than 8 volts, it's 0. So we're really only interested between 8 and 13. So things to note, how long is this? This is 13 minus 8 is 5. So if it's 5 long, so this is just probability on this side. My height's just going to be 1/5 or 0.2, whichever you prefer there. Because 5 times 1/5 is equal to 1. So it's the idea of if you cut a pie into fifths, you need 5 people to eat 1/5 to get the whole pie eaten. Of course, that's not how I eat pie, but... So to the question, find the probability the voltage level is less than 9 volts. So probability x is less than 9. That's still the same as saying probability that x is between 8 and 9. Right, so here's 9. Obviously probably not drawn to scale. I want to know the probabilities in between here. So for me, first thing I'm going to do, oh, how wide is this? 9 minus 8. Oh, that's convenient. It's 1. So, and my height is 1/5. So my width times height for my rectangle is going to just be 1 times 1/5. So 1/5. Or 0.20. So there's a 20% chance that if you randomly selected a voltage in here, that it would be between 8 and 9 volts, given this distribution. So absolutely, I strongly recommend, I'm super visual, so it helps me to draw out the rectangle. A lot of folks feel a lot more comfortable drawing out the rectangles than maybe using some of the equations. Either way, totally welcome. You should definitely get to the same place, no matter what you use. So still, same problem here, between 8 and 13 volts. And it is important that I label volts. It's less important that I write probability here, but it's still there. So, same problem, but now I want to find the probability the voltage is between 11 and 13 volts. So, that it's at least 11, right? We know it's 0 out here, so something like this. So probability that x is between 11 and 13 volts is equal to, so we knew the height here is 1/5, and the width here is 13 minus 11 is just 2. So we'll have 2 times 1/5, it's just going to be 2/5. Or 0.40. So a voltage level is above 11, but still under 13 about 40% of the time in this circuit. So now it's your turn. There are a lot of good bonus examples. I did try and make sure that they have hyperlinked solution buttons, so those work. At least I know when you have the slideshow open. So give those a try, and I look forward to hearing from y'all on the discussion boards.